Uh, I guess on last Thursday we talked a little bit about Eli. Let's do this. This is silly.
While Eric's getting this set up, there's a fellow out of DC who runs a fishing atlas website for anyway, he's the last couple of years organized a run forecasting competition for salmon. This year they're doing a bunch of sockeye runs in Alaska and elsewhere, and there's $5,000 in prize money. If anybody from class would like to enter, try out your time series skills. You may do it as well as everybody else.
Are we competing against all of you?
No.
I know, so okay. So she works for WDFW. Curry Cunningham, he's a professor at Alaska. Banks, Brian Burks, and Noah Fishery.
They're part of the competition. Oh, that's fun.
I don't quite know how that's working because like Brian's a Fed. Some people from DFO. So, yeah, somewhere.
But like Curry and Dan Avondo and some of the folks that used to be at SAFs, 10 years ago, they were thinking a lot about this problem in the context of forecasting sockeye returns to Bristol Bay, and I think they've written papers on that and using lots of different kinds of methods, and so I think I wouldn't want to compete against Curry.
Except no one's they're never right. So
yeah.
Might as well enter.
Yeah, maybe. Well, on that thread, today we're going to talk about another kind of tool in your toolbox for forecasting competitions, and that's generalized additive models. These are generally not really used for time series very much, but they are really common in all kinds of data science. So it's worth talking about them and then kind of making the bridge to dynamic linear models, which Mark talked about a week ago on Tuesday. So just to kind of the path that we're going to go through today, kind of a quick overview of what are generalized additive models or GAMs. We'll talk about some of the jargony terms. So what are these basis functions and smooths and knots and things like that? Differences and similarities between GAMs and dynamic linear models and how they can both be set up, if you're careful, to do the exact same thing. Next, we'll talk about GAMs and time series analysis and then kind of move on to some applications of GAMs. I should say, too, that this is going to be kind of in two parts. Today, we'll talk about GAMs in kind of a univariate context, and then kind of the links between GAMs and DLMs. And then on Thursday, we'll kind of extend these same ideas and talk about GAMs in the context of multivariate time series methods. And so thinking about GAMs in the context of DFAs and Mars models, where we have multiple time series that we're modeling simultaneously. Okay, so what is a GAM? GAMs are just extensions of linear models or GLMs that allow us to model complex nonlinear relationships between response variables and predictors. Okay, so they're slightly more flexible, but basically, if you get down into coding these up yourself, they're essentially the same thing as you would do with a GLIM or a mixed model. The basic formula that you'll see in textbooks for GAMs is something like this, where we have our univariate response variable on the left. We have a global intercept with beta naught, and then we can have any number of covariates here. And instead of in a GLIM setting or a linear model sense, we would have fixed effects coefficients for x1, x2, et cetera, out to xk. But here we are going to replace those fixed effect coefficients with some smooth function. So this f sub 1, f2, et cetera, out to fk. Those all represent different smooth functions of those predictors that we're going to be including in our kind of estimation process. So GAMs are super powerful, as I said. I think that probably the number one reason why I think they're really great is that they're so accessible. And so if somebody gives me a data set and asks me to explore something with it, because the formula syntax is so compatible with GAMs and GLIMs and GLM, MTMB, and all these other packages in R, it makes it very fast to be able to go from getting a data set cleaned up to fitting a model. It's also really flexible in that we can include nonlinear smooths between our predictors and the response. Third, all of the models that we're talking about in this class to date have been in this linear model context with normal observation errors, normal process errors. GAMs are flexible because we can include the entire GLIM set of families. The complexity, all the smooth functions that we had on that last slide, F1, F2, et cetera, those might represent different relationships with different predictors, and each of those might have a different kind of curvature or smoothness to it. And instead of iterating through with brute force kind of what are all the possible options of what those shapes might look like, it makes it really easy, especially in MGCV, to automate that process and estimate all of those relationships internally. I will add too, in addition to MGCV, there's other R packages that allow us to extend these models, including autocorrelated errors and complicated random effect structures. That's kind of beyond the scope of what I'll talk about today, but be aware that those are out there. Okay, so as I said, smooth functions and GAMs allow us to model nonlinear relationships between our response variable and predictors without having to specify what that functional form looks like. So if we were fitting a GLIM or a linear model, we could include a polynomial response, for example, between a covariate and a response variable, but we would need to specify a priori what the degree of that polynomial was. So we could make it a third order polynomial or a fifth order, but we would be each of those models would only fit one combination, and it wouldn't be exploring what alternative shapes might look like. So the smoothness in a GAM is controlled by this penalty term, and that's useful to avoid overfitting. So if you have sparse data, you don't have a lot of time points, then internally what's going to happen is that you're going to put a greater penalty on complexity, and it's not going to let you fit a really complicated nonlinear relationship. On the other end of the spectrum, if you have thousands of data points, then the model is going to be really relaxed and let you fit potentially very complex relationships. There's a number of different common kind of smooth functions that are used in GAMs. We'll talk about splines today. These are very similar to some of the other terminology you may have heard about: kernel smoothing, local regression, and Gaussian processes. And so Gaussian processes we can actually implement in MGCV, but these are all different approaches for smoothing data, doing kind of local smoothing of data, where you allow the predictions at any point to be affected most heavily by your nearest neighbors. Okay, so as I said, the linear models are just, everybody's seen this probably a lot of times. The GAMs are kind of replacing those fixed effects coefficients with these functions, and that flexibility allows us to capture potentially some really complex trends in the data that we can't describe normally with the linear model. Okay, so to implement this in MGCV, I guess I should say too, all the material that we'll be talking about today is going to be with the MGCV package in R. On Thursday, we'll switch to a couple of different others. I would also add, for anybody doing Bayesian modeling, the BRMS package in R is a really powerful way to interface between R and STAN and do Bayesian estimation. And I think all the models that we'll be talking about today are also things that you can fit using BRMS, because BRMS adopts the same kind of syntax for smoothing these covariates. And so the smoothing syntax, if you haven't seen this before, I'm sure most of you have, is just with this S notation. And so the S denotes the smooth. X1 in this case is the first variable that we're going to smooth over. BS means what kind of spline basis are we going to be using? In this case, the CR is kind of one of the defaults. This is just cubic regression. And then K denotes the dimension of that smooth. We'll talk about that in a little bit more detail. In this case, we're going to have two additive smooths, just a smooth of S1 and a smooth of S2. They're going to have the same dimension and the same basis, and we'll talk about the complexities of this in a little bit. Okay, so going backwards a bit, so what are splines and how do they fit into GAMs here? So splines are just piecewise polynomials that we can use to describe the variability in data sets, especially in thinking about data sets over time. Why are we going to use splines? They allow these curves to be flexible. We're not specifying the shape a priori. So the model is essentially learning what that curve might look like, and that curve can adapt to new data patterns as we collect more samples. It's also got this penalty term, which is great because it helps penalize overfitting by placing these weights that I'll show you close to zero. So it's essentially like a regularization term. And there's a number of different kinds of splines. They come in lots of flavors. B-splines are one of the most popular options. These are really commonly used because of their just flexibility and efficiency. Cubic splines are also very flexible, also widely used. Thin plate regression splines are kind of the default in MGCV. These all will do, for most data sets you encounter, these will all do essentially the same thing. So splines are one piece of this puzzle. Another are these knots. And so if you've done any kind of, I guess in most cases in fitting a GAM, we don't ever have to specify the knots, which is great. But the knots define the location of the curve that we're going to be used essentially as anchors. And we're going to be describing what that curve looks like between these knot locations. So if you've done spatial modeling, as I'm sure, as several of you in the class already have, you also have to think about this knot problem in 2 dimensions. And so you want to have the knots. I guess we use the knots because estimating a curve at every value of a potential data set can be really computationally inefficient, especially if we have hundreds or thousands of data points. So if we can instead estimate what that curve might look like, this complicated polynomial might look like at a subset of locations, and then based on the function values at those subsets, interpolate to every place else on the curve, that will be a huge computational gain. So we're going to be using these knots to approximate what this entire curve looks like at a subset of locations. There's a number of ways that we can define these knots. Again, we're not going to specify the knot locations by default in MGCV, but there's a couple ways to think about doing this. And so one approach is to think about distributing the knots evenly across a data set. And so if we were dealing with time series data, you could imagine that if we are collecting observations sequentially over a number of years, we might want to just distribute the knots evenly over that time set or over that time series. The other approach, and that's the default in MGCV, is kind of this data-driven placement. And so instead of having, if you think about the time series, if you had samples that were not collected uniformly with respect to time, that there's changes in survey effort, there's changes in other kind of external drivers that are affecting when surveys can occur. So we end up with kind of this data that's kind of clumpy. And so in some years we might be sampling heavily for 5 years, and then surveys might start happening every 2 or 3 years. And so for those kinds of situations, we're going to be wanting to have more flexibility, maybe where we have more data to estimate potentially more complex relationships. Okay, so this is we're going to kind of walk through how this looks like and what we're going to be doing here. Each of these colored curves here represents what's called a basis function, and we're going to be using these basis functions to describe to basically build a spline. So the basis functions are kind of the lowest level building block here. The x-axis represents our covariate, in this case just x. The y just represents the function value. It doesn't really matter. The range here is between 0 and 1. That not important. What is important here is that each of these has kind of a shape that can be described with the polynomial. And we can, in practice, you rarely have to actually adjust the complexity of what these basis functions look like, but that is an option. And then the other important part here is that if you look at each of these curves, so just focusing on like this dark purple one, at some point they have what's called positive support, so the function value is greater than 0. But at some point, if you look at each of these curves, that function value will go to 0. Okay, so these are basis functions. They are they're generated over the entire range of our covariate x. And then a priori, for this example, we're specifying that there's going to be 6 of them. And so there's 6 colors just ordered left to right. Okay, so now we've got those basis functions. We are going to be using them to build these B splines. Okay, so the B splines are going, each of, like as I said, I guess I just repeated the last slide. These are just kind of piecewise polynomials. We can adjust the smoothness or wiggliness of those, but rarely have to in practice. And these are always going to have some positive support and some place on that curve where the function essentially is becoming 0. To combine the basis functions then into a spline, in this case we're building this B spline, this is very easy. We're going to have these weights, which are going to be W. And for any value of x, if we know the value of the basis functions, so we had 6 basis functions, if we know the value of the 6 basis functions, which is b sub I, at each of those x values, and we have these weights, we can just multiply the weights by the basis functions to get our total prediction. Okay, so this is just going to be taking a weighted average of those basis functions. The weights are going to be estimated internally in the GAM. And the weights are also going to be constant over the range of the covariate. And so if this is a time series or any other covariate, over the range of that, the weights are going to be static. So the weights don't change. In this case, we would be estimating 6 parameters, 6 weights, and the basis function, essentially the basis function matrix that that is used to describe those 6 curves. That's something that's going to be automated and something we don't have to calculate ourselves. But you can think about it as being passed in kind of internally in the estimation phase here as data. So that's not changing. Okay, so this is what this looks like, going back to our example. So this weight vector here is just going to be used, and it's essentially a 6-element weight vector. We are going to be going through sequentially every value of x. And at every value of x, we are multiplying that weight vector by the corresponding value of the basis functions. So at the beginning of at the low end of x here, the basis function that's going to be contributing most of the weight is going to be basis function 1. And so maybe that's why we see this blue curve, which kind of represents the spline. This looks mostly like that dark purple. If we move over to the other end of the curve over here, we see this green spline at the end is getting the most weight. And this is, you can see it's the opposite direction, but that explains really why the spline is both large in magnitude and negative. So that's kind of the example with how we combine these to build a spline for this example with 6 basis functions. Okay. So what happens when we make the basis dimensions smaller? So this is something we're specifying a priori. We have to specify the basis dimension when we're fitting this GAM. We don't have to. It's a good idea. So if we make the basis dimension smaller, so we had 6 curves. Now we go. What happens if we go to 3? So now we have just 3 weights that we're going to estimate, and with that weight vector and these 3 basis functions, this is kind of what the prediction looks like. If our time series or our data look slightly different, we change the weight vector, we would get a different curve. And so in this case, if I go back, So in this first example, the third, or the weight is the largest for the third basis function. And so that, I think at the end of the time series, that explains why the spline is increasing here. But at the beginning of the time series, it's more tracking what's going on with that first curve. Okay. So you can make the basis dimension larger too. And so, this is an example where we go from 6 weights or six basis functions to 12, and the blue curve representing the spline gets more wiggly. And so the penalty, oh yeah, Ben.
So is this in some ways like a prior, like you need to have some prior knowledge of what you expect the shape to look like to set what your base functions are?
Totally, yeah, yes. I mean, I think it's not necessarily prior belief, but I think a good example would be let's say you're modeling fish survival as a function of temperature. And so you could think that maybe that relationship might look like it's probably like concave or something, where fish are not going to survive at either extreme. And maybe in the middle, you don't really know what's going on, but it's your decision about is this kind of shape plausible at the top of the curve? I would say probably not. It's probably going to be something that's much more smooth and probably something that's, maybe a third or fourth order polynomial, but not something that's that complex. Other questions? That's a good one. And it kind of unfortunately, it's not the kind of prior thing. I mean, you can think about it and sketch out your hypotheses a priori, but I think often you have to look at the predictions and then kind of refine the model after the fact. Okay, so on that thread, if we want to control the dimension of that penalty or that complexity of that model, we can do that going back to our original example by specifying this k parameter. And so k defines the number of basis functions that are going in here. And k is also closely related to the number of knots, or the number of points that we're approximating that curve at and interpolating to the rest. So for the example, for this example, k is 10. So based on our previous slide, this is 12, but if we're modeling fish survival as a function of temperature, and this is what the estimates look like from our function with 10 basis functions, that's probably too complex. So to fix that, what we could do is, after fitting the model, we could go back, we could change k from 10 to maybe 4 and refit it, and that would probably give us a curve that would probably be in line more closely with kind of our initial hypotheses. Okay, so there's a number of ways, this is really into the weeds. If you ever did want to take a GAM and extract what those basis function matrices are that generated those 6 or 12 curves that we were playing with, you can do that by using this smooth con function, and that gives us that will give us the matrix of basis functions that are being used internally. In practice, it's not the kind of thing that we have to ever really deal with that much. But why this is important is that we could take that basis function matrix, and you could think about using this as input for data into a regression model. And so we could just, in this case, I'm just generating some silly response data with y here. But then we could take our spline matrix that we pulled out of MGCV, and we could feed it into LM. And this would be giving us something that would be it would be really flexible. It would be estimating weights just as a GAM does. It would allow us to change the dimensions of that spline matrix to fit more wiggly shapes. But it's not doing exactly the same thing as MGCV, because what this is doing is there's no, you can think about the weights here are not going to be penalized. The weights are just going to be estimated as these fixed parameters on each dimension of the spline. In MGCV, though, there's a penalty. And so there's, the further the weights are away from 0, there's a greater penalty. And so in this case, this is spline regression. It's not going to give you the same output because we're not using the penalty matrix that MGCV is. Okay, so the take-homes with the splines and basis functions here are that we can fit really flexible curves using a very small number of basis functions. This is something that's often iterative, that you probably want to fit several different models and explore several different numbers of these basis functions. The flexibility in these models in GAMS is controlled by the number of knots and the knot placement. It's defined by the number of basis functions. That has a huge impact, as we saw going from 3 to 6 to 12 really changed how smooth that curve was. And I think a convenience of MGCV is that a lot of this is estimated internally, and so the basis functions, too few will lead to underfitting, too many overfitting, and because there's this penalty in there, I think that really helps with kind of estimating that dimensionality. Okay, so that's the spline part. The knots in the basis function, as I said, define where the individual pieces of that spline connect. And the next thing I want to talk about on the knots side of things is kind of going back to that. Where do we want to put those knots in the context of the data that we collect with the time series? So again, this is not something that we have to specify with MGCV. This is something that's done implicitly, and it's something that is by default is going to be distributed kind of in proportion to the data. And just like with the basis functions, the more knots we add, the more flexibility we're going to allow in our curve shape, because we're going to be interpolating over smaller and smaller ranges. And you can think about, in the context, especially in the context of these spatial models, we think about each time we add a knot, we think about adding a random effect. And the same thing is true here, where every time we add a knot to our time series, we're going to be adding essentially dimension. One more element is going to be estimated for this vector of random effects. Okay, so like with basis functions, fewer knots can lead to smoother curves, but also potentially underfit the data, versus adding more knots can also be overfitting. So it's really affecting, just like with basis functions, changing the number and position of knots affects how well our spline can match the data. Sorry with this. Example, again, there's just some simulated data. Again, fish survival and temperature. We've got, most of our data is clustered here, kind of below the mean on the left side of the plot. And then once we get to these higher temperature values, we start to see the data becoming much more sparse. And so I want to compare two different models, one where we have the knots evenly spaced, and then a second model where we have the knots kind of distributed based on the density of the data. So this is what the default knot placement looks like coming out of MGCV. And so this is distributed in proportion to the data. We've got, again, most of our knots are clustered where that high density patch is on the left. And then once we get to the tail over here, you can think about, there's almost like 10 points, 10 purple circles in each of these different bins. Where the data is really sparse, these knots are really spread out. So this is a ugly plot, but the red vertical dash lines here represent the even knot placement. And so this is just being agnostic to the density of the data, just uniformly distributed across the x-axis. The same number of knots is used in each case, and the predictions are basically identical. The mean predictions are falling right on top of each other. There's slight differences in the standard error of those predictions, but essentially, the point of this is that in practice, this doesn't really mean that the location of the knots is not going to probably affect your predictions very much. Okay, so when does knot placement matter? I think if your data are really unevenly distributed, then that can be an issue. If your relationship is nonlinear, and so I think if that curve between survival and temperature was really simple, it's essentially a concave second, third order polynomial. If it was much more wiggly, that could be a problem. Or if there was a regime or change point in that temperature survival relationship that really where we needed a higher density of knots around that location of where that regime happened, that would be a case where we would probably want to probably distribute the knots kind of in a non-random way. Okay, I talked about this a little bit. I'm not going to get into this. The splines just come in lots of flavors. I think that you'll see B splines are really popular. B splines and P splines are kind of an alternative to B splines that also include regularization or a penalty for complexity. The only real one I'll talk about here that's really useful for time series data are these circular splines. And so if you have data that is say monthly data, and you have data over 10 years that's monthly, and you want to fit a GAM to those data, and you want to include a seasonal pattern, the circular spline is really helpful there because it allows you to connect predictions in December to predictions in January, and so that's a January the following year. And so because of that, I think that if you're ever dealing with seasonal data in a GAM, the circular splines are probably the best way to do that. The rest of these will give very flexible shapes for year effects, say, but they won't be able to make that connection. Okay, so moving on. So that was kind of the introduction of GAMs. Now we'll talk about kind of using GAMs in time series. So we've talked a lot about state space models, and GAMs have similar flexibility. They're not going to be partitioning the process error and observation error in the same way that state space models do. So we'll be able to estimate, depending on the response, if our response is normal, we'll be able to estimate an observation error, but we're not going to be pulling out a process variance the same way that we can with a state space model. But otherwise, they're super flexible. They can allow us to model a lot of these complex relationships in data, including smooth functions of time. They can handle seasonality, and talked about the cubic or the circular spline. But all of those monthly, yearly, seasonal effects can be incorporated just as we do with time series. And we can incorporate, I guess we can incorporate random noise in our data with random effects and other complicated structures. So there's lots of flexibility here. But if the focus of your inference is going to be on any of the process variants or these process deviations, GAMs probably are not the best way to go. As an example of something that came across my desk in the last few months where GAMs were really useful, I had somebody send me data that was sort of like this. This is not exactly this data set, but this is these points represent shad counts, a species of invasive fish on the Columbia River, just for 3 years of data from 2022 to 2024. So these are daily counts. I think that most of the shad run is in summer, and the biggest issue here is that we've got these 3 years of data, but there's these huge gaps between the end of the summer in the first year and the start in the next year. And so you could certainly fit these models using univariate state space models. That's totally fine. The challenge is that when you do that, you're going to be estimating a value for x of t for every, this daily counts for every day that is, in this window and in this window. You're going to be estimating kind of a value for that x of t, and the uncertainty as that as that random walk gets further and further away from data, the uncertainty there really balloons, and so we're going to get really big errors, and we're going to be estimating parameters that we probably don't need to actually be estimating, because we don't really care about our predictions in this window. If shad are not counted here, they're not in the system. We don't really care. So this is the kind of data where GAMs might come in handy, because we can fit alternative structures. So I'm not going to be talking about this example in much detail, other than we can set up a model like this, where we have kind of the log of shad abundance is our response. We have year factors, which allow each predictions in each year, essentially the curve height, to be shifted up and down. And we can model some smooth effective Julian day that's kind of shared across years. This is a simple example. This is only 3 years of data, but on Thursday, we'll talk about how to approach these kinds of data using kind of hierarchical models and hierarchical GAMs. Right. I would say, I'm sorry. I would say just as a first pass, this is the kind of thing that you can get set up very quickly. I said GAMs, one of the pros is really their accessibility. So this model, even though it's fairly simple, gives really good predictions. And so if we just calculate some rough correlations between observed and predicted values, we're almost at 0.9, which is really good. Okay, so that's that's an example of why we might use a GAM. Next, I want to move on to kind of going back to what Mark talked about a week ago and thinking about DLMs in the context of GAMs. And so this is a data set that is kind of already included in R. It's this economics data set. It's got 10 different variables in it, but we'll be pulling out just a few of them. And so there's a personal savings rate variable called this first one, P-save rate. There's unemploy, which is the unemployment rate. And then there's a timestamp or date of each of these. And just for simplicity, or just kind of data wrangling, we'll just convert the date to a number, and then we'll also deal with log of unemployment because it's really heavily skewed. Okay, so what do these data look like? Kind of a priori, we might think that as unemployment rate goes up, so unemployment is the bottom plot here, as unemployment goes up, we might expect to see folks' personal savings are basically stashing more and more money away. So we might expect to see similar patterns with savings rates also increasing as unemployment rate increases. And so these are just some smooth fit to the raw data, but in general, that trend might be happening here, where we see, or maybe it's, I don't know, maybe it's the opposite. Unemployment rate increasing here, that's kind of corresponds to low personal savings rate. And we're going to be modeling these in tandem with personal savings rate is going to be our response variable here. And this is a time series. And the time, I think these are days since whatever the reference day was. I think this data set started back in the 1980s. Okay, so the first model here is going to be fit where we're just going to model personal savings, and we're going to include a smooth or a spline on time. We're not going to specify the number of basis functions. We're just going to let MGCV estimate that or try to approximate that for us with the default. And we'll just use this cubic regression basis functions. So with this kind of model where we're just modeling savings rate as a function of time, what is this model doing, and where have we seen this before? Let's think about what Mark was talking about on Tuesday. So this is a flexible model. We're including a smooth over time, and we have a single response, which is just our personal savings rate. Anybody want to guess? So all we're modeling here is going to be, we're modeling the mean, right? So we're letting savings rate vary and time. We're basically letting savings rate vary over time, where we're just thinking about letting that intercept vary over time, right? So this is really similar to, if we fit a smooth over time, it's really similar to just letting the intercept vary over time. And if we're letting the intercept vary over time, that's really similar and exactly the same, actually, as what Mark talked about with kind of these DLMs where we just have intercept-only models. So if we look at the predictions from this model, this is basically capturing the level of that personal savings rate variable over time, right? Because we saw it start off high at the beginning of the time series, and then it kind of went down towards the end. So that is this model, where we just include a smooth over time, is just capturing the overall level in the data, right? So that's a super flexible approach that is a good kind of first pass. So this model, if you wanted to fit or compare an intercept-only DLM to a GAM and make that direct comparison, this is the model that you would fit. Okay, I showed this. Okay, so it gets a little bit more complicated if we want to move on from the intercept-only model and think about using GAMs to fit models where the covariates are varying over time. And so I think in the DLM material that Mark was talking about, we talked about DLMs where the intercept only varies, DLMs where the slope is the only thing that's varying, and DLMs where the intercept and the slope are varying at the same time. Okay, so if we want to switch gears from an intercept-only model, let's switch gears from an intercept-only model, hold the intercept constant. So there is a, just like with all GAMs and LMs, there is an intercept here that's estimated implicitly. But aside from the intercept, we're just going to we want to say that there's going to be a time-varying effect of unemployment. Okay, so one way to set this up is to set it up this way. We'll just say that savings rate is going to vary as a function, the smooth function of unemployment. Everything is the same as before, and we have this global intercept that we're estimating. Okay, so what is this? Does anybody take a stab at what this model is doing? Savings rate is a smooth function of unemployment. This is sort of like when I was giving examples of modeling, say, fish survival as a function of temperature, right? And so in this case, if we're modeling fish survival as a function of temperature, we don't really care about time. And so the same is true here. If we're modeling, if our smooth is over unemployment, and we only have a global intercept, this is essentially what's happening. We have our covariate, so log unemployment is on the x-axis. The predictions of that smooth are on the y. And we can get the total predictions by combining these smooth effects, these smooth marginal effects, with a global intercept. This is all in log space, and so we can back transform. But essentially, this is the smooth relationship where there seems to be some kind of curvature happening over here. But after, once the log of unemployment rate is above 8.7 or something, that curve is basically flat. So it's a flexible relationship. It's super smooth. However, it's totally ignoring time, right? Okay, so this is not exactly what we want. If our goal here is to develop a time-varying effect of the covariate, this is not really going to help us. Okay, so to do that, we could try to just think about throwing other things in there to get MGCV to do what we want. And so this first thing that what we're going to do next is we're going to add time into our smooth of unemployment. And so you'll see people talking about these higher order, you can include second and third order smooths in MGCV very easily by including other covariates in that term. People do this, this is a two-dimensional example. People do this all the time with three-dimensional examples. If you have, say, a latitude and longitude dimension, you're fitting a spatial model, and you have a time dimension, then all of a sudden you can include a smooth with three different terms. So, our goal here is going to be to let unemployment vary over time, and so we're including this two-dimensional smooth, which is very flexible. But let's think about what this thing is doing. And so it's going to be fitting a smooth surface where we have time on the x-axis and unemployment on the y. And it's estimating a smooth surface over that two-dimensional grid. And if we squint, I think this it shows up better on my screen than it does here. There is kind of a high point over here that's a little bit more orange, a little bit more yellow. But in general, this is essentially one-dimensional. There's essentially a kind of a one-dimensional gradient for both directions here, where there's not a lot of contrast. We don't see a lot of peaks and valleys, and so what this wants to do, I guess, what I should say is that this is in terms of estimating the interaction. There's not much of an interaction here because each of these covariates is only changing in one direction. We could imagine, let's see if my slide will go down. No, that's the next one. Yeah, there we go. I guess like my slides are only, let's see, sorry, this is. So in some cases, we might see with a two-dimensional smooth that looks something more like this. And so in this case, this would be an example where these two covariates, x1 and x2, had a lot of interaction because this is not a very smooth gradient. It's got lots of peaks and valleys where the combinations, the particular combinations of x1 and x2 really decide whether this interaction is going to have a really strong positive or a really strong negative effect. Okay, so going back to our time series example, this also creates this super flexible model. We're estimating this two-dimensional smooth now, but these smooths are also static. There's also there is this time dimension, but we're really not letting the unemployment vary in a time series type way. We're letting, for this particular model, because there's a gradient in one direction and a gradient in the other, we could look at the marginal effects and see that there was some slight effect or some slight change over time, but it's not going to be the same kind of flexibility that we would get from fitting like a DLM. Let's zoom out here and see if that shows up better. Okay. So that 2D smooth includes that interaction, but it's not going to be estimating the same kind of dimension that we want for that time varying slope. Moving on to the next kind of model that we can fit, we can use this smooth term and we can include the by word. And so the by argument is kind of a magic word in MGCV. And that lets us fit different smooths that vary by whatever the covariate is that we want to vary that smooth over. Okay, so the first argument, the predictor, is going to be our variable of interest, and then the by is what we're letting it change over. So let's do this now with our time series of savings rate and unemployment. So the way that we're going to set this up is we're going to model savings rate as a function of unemployment, the smooth function of unemployment. And just as the first pass of this, we're going to be using time as the by argument, okay? So what is this doing? This is letting the shape and the smooth of log of that unemployment vary by time, which sounds really flexible, and it is really flexible, but it's not really preserving the order of these of these time steps. And so what's happening here is that it's estimating for every different year of our time series, it's estimating a different effect of unemployment, but it doesn't really care if our time steps are sequential. And so it's not going to be, when we plot the effect of a time varying slope coming out of a DLM, we get something that's really smooth, and neighboring time steps have predictions that are very similar. This is not doing that. This is letting each time step is going to be very flexible. It's going to have essentially not exactly independent estimates, but something that's closer to that. And this is what the curve would look like coming out of that model. So when we put that smooth over unemployment and say by equals time, the curve that's coming out of this is going to be looking like this, where unemployment is on the x-axis, the predictions from the spline on the y, and we get we get something where where we have a lot of data, we get predictions that are pretty similar. But in other regions, especially at the beginning of the time series, things are jumping around a little bit more. Okay. So one of the things we can do though, and this is it took me a long time to figure this out, but if we change the order of the arguments, I guess the order of the arguments in MGCV is a little bit backwards from at least how I think about it. And so if we change the order of these arguments and say, instead of fitting a smooth over log of unemployment, and we do that for each value of time, we're gonna fit our smooth over time, but we're gonna let that vary by every value of our unemployment variable. And so in my head, naturally, I have these switched. And so you'll see here, we're going to have the smooth over time for each value of our unemployment. Okay, so yeah. Can
you go back? Is this, that one. So is this curve, does that curve like vary depending on what time step you're at? Or is it time on the x-axis?
Unemployment is on the x. And for each, for each value of time, it's going to be letting that change. Yeah.
Okay, so that looks different. And then how is, I'm not understanding how that's different from that like plot you showed before, that like density plot with x1 and x. Like that.
Yeah. So this is essentially a super flexible two-dimensional regression where you could have two variables. Like you don't need GAMs to do this. You could come up with a let's say you did a third order polynomial. You have x1 and x2, two variables, and you created combinations of each of those for their linear combinations and quadratic combinations and maybe third and fourth order, and made this giant polynomial matrix. You could estimate the same kind of thing. So this is just estimating the interactions between x and x1 and x2. And it is, in some ways you could think about if x1 is time, you could think about finding the place on the map for your given value of x1 and see, I guess you could look at the cross section of that to see what the x2 would change over time for sure with that interaction, but it wouldn't change in a way that was necessarily smooth. And what I'm trying to get to is a point where we have something that's smooth and varying in time the same way that DLM is. So this is going to give you, it is really flexible. These are totally valid models for some situations.
But this is just less smooth than when you have the bi. That like makes it more smooth in one direction or something?
Yeah, we're going to be only fitting that smooth effect over time, and we're going to do that for basically each value of the covariate. Yeah. Let me walk through an example, and then we can come back to it. So this, I think on that thread, I think that one thing here is that when we think about the DLM, the DLM is modeling the time, or the change in the slope every time step is just controlled by a normal random walk. And so the deviations for, as we kind of march through the time series, the deviations are all about normal. And that means that the smoothness is going to stay similarly smooth over the entire time series. And you can see when we plot like unemployment coming out of, when we use time as the bi argument in the GAM, we get something that's quite a bit different, where things are really not changing in this kind of core part where we have a lot of data, versus relative to where data are sparse, things are uncertain and changing quite a bit more. So I guess the year-to-year change or time step to time step change would be different in this situation versus what we are trying to get out of with the DLM. Okay, so let's make smooth. The smooth will be time will be first, and unemployment will be our by variable. And what we get out of this now is something that is really similar to what we kind of expect coming out of a DLM, where it's much more gradual. We've got the standard error is not changing over the time series, and so this is similar to the DLM. We can change the wiggliness of this. I didn't include the number of basis functions in this argument here, but after we say by equals unemployment, we could add k to specify the basis functions if we wanted. We thought that this was too smooth and wanted it to be more wiggly. That would be kind of how we adjusted that. Yeah.
So how in just like layman's terms, how would you interpret this figure?
I would interpret this to be the kind of marginal prediction of the time varying effect of unemployment on savings rate. And so the way I would interpret this would be savings rate would be, or the marginal effect. With that example, unemployment has a positive effect on, unemployment overall has a positive effect on savings because it's all of the values of this curve are positive. And then at the beginning of the time series, we see the strongest effect. So in the beginning of the time series, we see higher unemployment having a higher effect on savings versus low. At the end of the time series, we see that effect still being positive, but that relationship has kind of broken down a bit. Yeah.
So for this, is this saying that that effect of unemployment is linear, but the slope varies, rather than being squiggly, and that squiggly is through time?
What's fun about GAMs is that squiggly and wiggly are you can the technical terms. Yeah. So they're not exactly linear, but they are going to be close. Yes, they're going to be like second or third order polynomials. Yeah. Other questions? Yeah.
I guess I'm not understanding. I feel like I understand what the by call is doing.
Mm-hmm.
In a case like this, where there would only be one observation per time step, right? Like there's only one unemployment rate per time step.
Right.
So how is it? What does it mean to go with by unemployment rate at each step?
So this gets back to the knots, right? Because this is going to be estimated. We're not specifying. I guess we're not specifying the basis dimension, but internally that's going to be calculated in MGCB, and so it's going to estimate. It's not going to actually estimate a value of that function for every single covariate value that you have, but it's going to estimate it. I mean, it's going to pick a number of knots that's like 10, and so it's going to estimate 10 of those functions. And it's going to say that in between those 10 spots, we don't know exactly what's happening, but we can predict based on, we assume everything is polynomials. We can, these second order polynomials, we can predict kind of, if we know what the knots are adjacent to the data, we can predict to the location of the data. So it's not estimating at every single spot, which is key. Okay. I just threw a ton of models at you. All those models are good models for certain applications, but for the purposes of time series and especially thinking about this link to DLMs, it's really the last one that's probably the most important. And so I thought, given all the models that we've thrown at you, it would be worth kind of thinking through what the impacts are on forecasts, because that's been a kind of something we've talked a lot about in this class. And so thinking about forecasts, the two models that I want to think about are kind of this non-linear model versus the non-stationary model. And so the the nonlinear model is the model where we're just going to model, say, personal savings rate is a function or a smooth of unemployment. There's no time. It's just going to model, in the case of the fish temperature example, that was just the concave relationship where we're going to totally ignore time. All we care about is that concave relationship. And so when we predict from that kind of model, where is the prediction going to fail? Like if we thinking about temperature versus fish survival, if we have data from between 8 and 10 degrees Celsius, and we can estimate survival smoothly over that range, where is that model going to fail in its predictions? What happens? Is it ever going to fail if our temperature is ever between 8 and 10 degrees? Is it ever? We're always going to be able to make predictions over that range because we have a curve. We've collected a lot of data. What happens though if our next observation is it's 12 degrees? We've never seen that before. So we're essentially predicting beyond the range of the data. If we think about that smooth, we're predicting beyond the range of the data. And I think we see in doing forecasts with the random walk models, we see the same thing. We see uncertainty really balloon. If we have a smooth relationship of one variable related to another, we get the same kind of effect where if we are observing kind of these novel temperatures, we have no idea what survival is going to be like. So that's where the nonlinear models fail. The non-stationary models fail, I think, or not, I shouldn't say fail. The non-stationary models are really challenged, again, when we're predicting beyond the range of the data. And so just like with a DLM or a state space model, we know that if we just stop surveying and try to make predictions in the future, we know that those models are gonna struggle because these random walks just have the variance is just going to keep increasing and increasing every year. And then if we start to try to predict 50 or 100 years in the future, the uncertainty is just going to be totally blowing up all of our plots. So thinking about these models and their challenges, one thing I wanted to point out, and this honestly every time I think about this it breaks my brain, but if we have these two models that are kind of competing, so we have, again, going back to our savings rate and unemployment example, if we fit this nonlinear model in kind of the pink line and the time varying model, the time varying DLM with the blue. So in this first case, we're totally ignoring time. We're modeling just that smooth. It's essentially analogous to the log survival as a function of temperature. Totally agnostic with respect to time. In the blue one, this is akin to kind of what Mark was talking about with the DLM, where we have this time varying slope that's varying, the effect of unemployment is varying over time. And these models give exactly the same predictions. They fit the data amazingly well. So the take home here is that nonlinear models and non-stationary models can do the exact same thing in terms of this is predictions to the data that we've got in hand. And a fun thing about this is I think that you can do a literature search, and there are papers where people have done these meta-analyses to look at, I'm just going to say not the ubiquitous of nonlinearities in ecology. And people have gone through and they will fit all these models looking at nonlinear effects. And these papers are published in good journals, but you can search, and not once are people looking at whether these kinds of models or the kinds of data might be explained instead by these time varying relationships. Okay, and so the same thing is true with the time varying literature, where people think a lot about non-stationary processes. That's a hot topic right now in ecology, without really thinking about whether the processes instead might be generated from these nonlinear relationships that are totally agnostic with respect to time. Okay, so for training, those two models give us essentially the exact same thing. So what if we do forecasts instead? And so to do these forecasts, I took that same data set, held out the last 20 observations, and tried to forecast those. And so the blue line here again is the time varying model. The red is the nonlinear, and we can see that both of the models give us maybe not great predictions. They're both off by a scale, right? Because there's this consistent bias where they're both overestimating the predictions. So I would say that the red one, the nonlinear model, does a little bit better, but it's these are both creating biases. What about uncertainty? And so this is forecast uncertainty again from both of these. The time varying model probably gives us a little bit lower uncertainty with the kind of the blue envelope versus the red, which is the nonlinear one. Again, these are both biased high. They both have uncertainty that's somewhat increasing as we go kind of march out along the x-axis in time. This is really similar to a DLM, but if we were to fit a DLM to these data, the uncertainty with the DLM, because of that random walk, that uncertainty is going to be higher than the forecast from these GAMs. Okay, so given that these models give kind of equally, we'll say, equally poor forecasts to those data, we might want to decide about how to decide between these two approaches. How do we decide if you have this in practice and you want to fit a model that's nonlinear versus one that's non-stationary? The implications for whether a system is in one of those two states leads you down two very different paths in terms of providing advice and especially around any kind of management decision about what should be done. So how do we decide between these two models that are competing where one's nonlinear, one's non-stationary? And so there's a number of different ways to do this. I think there's a number of kind of these standard diagnostics that I think that folks have probably played with in different settings. We can calculate these all here, and there's kind of I wrote a simple little function that's available in the slide deck to do this. But we can calculate all of these model selection tools for kind of in sample and then predictive performance for these models. So the first row here is just kind of the nonlinear model. The second one is the time varying model that's akin to the DLM. We can see, so AIC, again, it's not the best statistic. However, lower AIC values are better. So we would conclude based on AIC that the nonlinear model, it kind of explains that relationship between unemployment and savings rate. The GCV is a generalized cross-validation approximation that comes out of MGCV. In general, the statistic that is lower is better. So based on GCV, we would conclude the nonlinear form is supported. R squared, we want to be higher. So that's a tiny bit better for the nonlinear. And then root mean squared error is, we want that to be minimized, like with AIC or GCV. So based on these kinds of statistics, one would conclude, I think, that the nonlinear, there's probably more support here for the nonlinear GAM over the time-varying GAM. You could also, and we'll talk about this more in a couple of weeks, you could also do some more detailed cross-validation to test this a little bit further and see where the nonlinear model might fail. But based on all of these statistics, I would say the nonlinear model probably has greater support. Okay, so time-varying slope versus time-varying intercept. I think this is a big thing to think about. I think it is not just something that occurs with GAMs, but also with DLMs. And based on our kind of experience, it's often really hard to fit a model that has both a time-varying slope and a time-varying intercept. And a lot of the reason for this is that the model, a lot of these data sets, I should say here, yeah. A lot of these data sets have some change in the level. So there's some pattern over a time series, whether it's survival or savings rate. There's some general pattern over the time series that's non-stationary. And the time-varying DLM, with the time-varying intercept in a DLM, or the time-varying intercept in a GAM, is going to really try hard to fit that general change in the level or change in the non-stationary pattern. So because of that, it can be challenging to also estimate the effect of the time varying slope. So one thing I wanted to do here was to basically set up. I think that there's the salmon survival DLM example that's kind of worked up in the Mars manual, and something Mark talked about. This is modeling salmon survival as a function of April upwelling. And we can set this up with two ways. And so in the first, we've done this with DLMs. Same thing here as with the GAM, where in the first model, that's akin to an intercept only, or the time varying part of this is going to be the intercept in the first model. And in the second model, we're going to be letting the effect of upwelling vary through time, again, because we're using this magic byword, and we're swapping year and upwelling as arguments. Okay, so these models, again, just like with the DLM, they both are super flexible. They both can fit the data, almost equally well, but they have really different, things going on. The time varying intercept in pink and the time varying slope in blue, are both really reasonably good fits. We could calculate the same statistics, the R squared, the AIC, et cetera, to look at kind of how those statistics perform. But I think probably more important than all of those statistics would be to do some basic, just looking at residual plots to help kind of decide which of these two models is more supported. And so pulling out the first one, this is kind of the residuals that are being pulled out of the time varying intercept model. And in general, I think that there is some clumpiness here. What we're looking for is, are these approximately normally distributed? Is there any clumpiness or kind of, is there any extreme values? Maybe there's a couple, but then again, are they correlated? And so though this says index, this is really going to be time. Are there clumps where there's high or low values that are clustered together that aren't really described by the pattern of the data? And I think for this particular case, this is probably okay. It's not great, but it's also not terrible. If we compare this then to the residuals for the time varying slope, I think this is quite a bit worse. Where at the beginning of the time series, we see a clump of really positive values. Kind of in the middle, there's some negative ones, and again at the end, we see positive ones. And what that's telling us is that the flexibility in the model that has the time varying slope is really not enough to explain the year-to-year change in that survival data. So what we end up with is kind of this, this autocorrelated residual pattern. And you could run any of the ACF statistics, et cetera, on this to calculate, what those autocorrelation values are. But this is generally more of a problem than, if I go back, the time varying slope was a little bit better behaved. Okay, so that's a lot. For this example, time varying intercepts, as I said, would be more supported than time varying slopes. That's something that we've come across with lots of this DLM work. And from the covariate perspective, there's a number of reasons why that time varying slope parameter type model might not be supported either with a GAM or with a DLM. And the reasons for that are that that we might not have enough range of that covariate. So for the purposes of thinking about upwelling, it could be that all of the upwelling values are close to the mean and that we don't really see the extremes. Seeing the extremes would really help identify that relationship and kind of what that curve might look like. So one is that covariate doesn't have enough variation. Second, the intercepts might not be, or the slopes might not be identifiable without priors, and so you could try this also in a Bayesian setting to try to constrain the estimation a bit. And I would also add that finally, kind of your ability to estimate the time varying slopes and the time varying intercepts is going to really change kind of case by case. It's going to be affected by all kinds of things like the observation error in your data, non-stationarity in your covariates or non-stationarity in your responses. And so, doing the diagnostics, in addition to the summary statistics, looking at the residual plots, et cetera, is really key for comparing and building models. Okay, that is it for today on GAMS. I think there's lots of other great references out there that I didn't include. Gavin Simpson has done a ton of work around GAMS and has a lot of great papers and resources on the internet. And then Simon Wood has a number of books that are really good for reference and really detailed reading if you really want to get into splines and basis functions and GAMS. All right, that's it. Yeah. Any questions?
I have a question, Eric. What's your experience with the performance of GAMS for forecasting?
I have not found them to be great because of, yeah, I mean, it depends again if you have covariates or not. I was thinking about, like, Eli and I had done this meta-analysis 10 years or more ago, where GAMS were thrown in the mix, and they didn't do great. Again, I think because you're predicting beyond, if you have a smooth on time and you're predicting beyond any time step that you've ever observed, you have the same problem that you do with a state space model. I think these are, like, the GAMS are powerful if you do have covariates and you have a situation that's more akin to the relationship between modeling survival, fish survival as a function of temperature, and you can ignore, if you ignore time, then you can make great predictions if you have temperature.
I'll just add to slide 36.
I can't see my numbers here. Let's see here.
Go forward. Back just one more. You have like this one more, maybe one more there. So those of you who are probably maybe working on your write-ups for the DFA lab, or you get to something you have to tell us what the latent trends look like. This is that same curse exists in games. So inevitably, people will fit models, and then a lot of the variance is being explained by these splines, and maybe not much by some covariate of interest. So then you have to try to tell us what that, like, if I'm going to describe that in a paper, it's not particularly easy, and it's largely capturing the phenomena of the data itself. Right, so Eric was alluding to, you start putting in lots of splines with lots of knots. I mean, holy hell, that thing, you can have an unbelievably squiggly, wiggly pattern, and it will fit that. So I think others would caution you to really think about keeping anything and only fit simple, especially with those smooth terms, because it will fit very well, but at some point it's probably overfit, and like I said, you have to explain what that is.
Sorry, Mark. Is there any objectives criteria for finding whether a model will be overfitted in that case?
I guess, well, I don't know about that for sure. It's hard to do the parameter counting. You can. And for a univariate response with not a lot of data, you'd have to, I mean, that data set that Eric was playing around with was what, 15,000 data points or something like that. It's a really long time series. I think you'd run in, you will get, not unlike when we did with DFAs, we talked about this thing that sometimes if you look at the loadings on them, you get a whole bunch of loadings that maybe half of them are positive and half are negative, and the trend doesn't really look like much. That's a symptom of overfitting. I'm not familiar with any formal examination of that, what that looks like. I don't know if Eric or Eli, you have any experience there. But Yeah, but it can, I mean, and like you said, how much are you trying to just chase some pattern in there versus come up with something that, maybe looks like a sine wave or something.
All right, sounds good. Well, we'll talk about this more on Thursday.